His talk will be combining ytterbium and lithium, Feshbach resonance, and dual species Bose-Fermi superfluid. I guess his talk is ready, so let's welcome Dr. Gupta.
Great. Thank you. And thanks to the organizers for putting together this great conference. It's great to be in Seoul. And thanks also for including this work in the program. It really is an honor to be up here. So the title of the talk is a little different from that announced. It's now two-element mixture of Bose and Fermi superfluids. So I will focus more on the latest work that we have from our group. To introduce these two elements of our Bose and Fermi superfluid mixture, I will first show you this periodic table of elements where I've highlighted the ones that can be brought to quantum degeneracy with standard cooling and trapping techniques. And within that, I'll point out that our fermionic component is the 6 lithium, over here in red, and the bosonic is the ytterbium here in blue. And you'll notice that they come from very different rows of the periodic table, meaning that their masses are quite different, about a factor of 30 different. And they come also from different rows of the periodic table, meaning their electronic structure is different. Lithium is in this group 1 alkali column. Ytterbium is languishing all the way over here in the end of the lanthanide series. But it really, at least for all intents and purposes for this talk and most laser cooling and trapping applications, is like a group 2 atom. It shares all the properties of a closed S shell. So experiments in our group and also those in a group in Kyoto, Takahashi's group, about 5 years ago showed that this mixture is a stable one. So it's collisionally stable, and further experiments could be performed with this combination. What further experiments could you do? What could you use with this? What could you take advantage of with this mixture to go beyond studies with single species? You could look at the large differences in mass and electronic structure and come up with species selective techniques, which could allow you to produce bath probe systems, so a minority component and a majority component. For instance, you could apply this towards sympathetic cooling applications. Conversely, you could use the minority species to probe some property of the majority species. In the context of pairing, interaction-induced pairing, the fact that you naturally have an imbalance between the two components forming the pair can bring significance to not only few but also many-body physics. And in particular, if you look at combining the pair into a molecule, the heteronuclear nature can give rise to polar molecules, which is a completely new entity. And it's a very exciting area of research now. And in this context, I just want to mention that the ytterbium-lithium combination, because it comes from group 1 and group 2 like atom, has a combination of electric and magnetic dipole moments. So it brings some new features into the cold atom physics, cold molecule physics that's going on now. So with further introduction to those atoms, lithium, I don't have to introduce much more. It was already spoken about in the previous talk and also in yesterday's talk by Randy Hewlett. The two lowest spin states has a beautiful magnetic Feshbach resonance centered around 832 Gauss. And this will be the area we will use to create our fermionic superfluid. Ytterbium, on the other hand, is this closed shell atom. And in particular, the bosonic isotope that we use, 174, has no magnetic moment at all. So it's completely insensitive to magnetic fields. And for a linked reason, also has no magnetic Feshbach resonances, no individual interaction tuning really possible with magnetic fields. And linked to this also is the result that this combination in the ground state possesses no magnetic Feshbach resonances. However, this atom also has some long-lived excited states up here, and this is linked to very narrow electronic transitions, which are utilized to make, for instance, very precise clocks, and now also for some quantum simulation applications like SUFN physics. The lack of magnetic Feshbach resonances in the ground state can be, one can try to assuage that by looking at the combination of an excited metastable state with a ground state in lithium. And we did that. And to briefly just show you this result, in combination with the excited metastable state, the anisotropy of the state induces magnetic Feshbach resonances. And here, as a function of magnetic field, I show an inelastic loss curve, which has magnetic field-dependent behavior. And in conjunction with our theoretical collaborator, Svetlana Kozhugova, this can be linked to magnetic Feshbach resonances in the system. We also have a molecule production agenda with the ytterbium-lithium system, and here I'm just flashing on this slide. I won't get into any details, but each of these peaks shown here are signatures of photoassociation resonances, formation of ytterbium-lithium molecules in the excited state, and details can be found in this paper here. Okay, so to get into some of the technical aspects of how we produce this two-element superfluid, I also want to cover related work, which is written up here. Our system basically is simple. You start with laser-cooled atoms. You throw it into an optical trap, and you do evaporative cooling in the optical trap to quantum degeneracy. We recently showed a way to make this process more efficient and faster. And how we did that was to, what you see here is our optical trapping beam traversing the chamber in this fashion to produce a crossed beam optical dipole trap. And the AOM over here controls the power, which then controls the depth of the trap for evaporative cooling. But in addition to controlling the power, we also we also frequency modulate the AOM. And doing that, we can create, we modulate the position of this optical trapping beam at the atoms. And if you do it fast enough, you get a time average potential. It's known as painted optical potential. So the idea has been in this field for a while. And using this painted optical potential, you get a new parameter which you can change dynamically during evaporative cooling. Not just the power, but also the painting parameter. And using those two knobs, you can balance out the two competing processes during evaporative cooling, elastic collision rate and three-body rates. And we found that if you optimize the system for speed, you can get down to cycle times of 1.8 seconds or so to create Bose-Einstein condensates of about 100,000 atoms, which, to our knowledge, is the fastest cycle time in optical traps. You can get a little bit lower at the cost of somewhat lower atom number, maybe 1.6 seconds or so. So this time scale starts to become comparable to time scales achieved in magnetic chip traps, but it is generally applicable to all kinds of atoms, also ones that are not magnetically trappable, applicable to fermions. And the implementation is relatively straightforward because you just need a single acousto-optic modulator, which is already existent in most optical trapping systems. And one can apply it towards precision measurements such as interferometry. You can optimize the system for large numbers, in which case we can get up to more than 1 million atoms in the Bose-Einstein condensate. And in fact, the optimization for number now becomes important when you want to extend it to a two-species system, because we're going to use the ytterbium to sympathetically cool lithium. So now focusing in on the two species setup, our wavelength is 1 micron, and that implies for the two species under consideration, the trap depth ratio is a factor of 2.2. And if you look at the mass ratio, that gives you a trapping frequency ratio of about a factor of 8. So it's a pretty large difference between the two. And this trap depth ratio and the fact that the ytterbium cloud, at least in the classical regime, is larger than the lithium cloud. So all the blue is ytterbium here, all the red is lithium. Means the natural choice for doing sympathetic cooling is to use ytterbium to cool the lithium, because the ytterbium will preferentially escape as you lower the trap depth. As you get to the quantum degenerate condition, though, the size mismatch reverses, and that's because the ytterbium gas is a boson, and it keeps on shrinking in size as you cool. The lithium gas is a fermion. It stays stuck after a while at the Fermi diameter. Okay, so using these techniques, we produce by an all-optical method Bose-Fermi mixture of a few 100,000 lithium fermions and ytterbium bosons at temperatures which are quite low. And here you have a basically pure Bose-Einstein condensate. How to get to the Fermi superfluid. And here I just provide a small backdrop, historical backdrop, saying that the idea of achieving Bose-Fermi combined superfluidity has been around for a while. It's been pursued in the 4-helium, 3-helium community, but because of strong repulsive interactions there, the combined superfluidity is not yet realized, though it's still an interesting research direction there. Recently, a couple of years ago, in Christoph Salomon's group, the first Bose-Fermi superfluid was achieved in a 2-isotope mixture of 7 and 6 lithium. And now in our system with the lithium-ytterbium combination, I will tell you how we make the two species superfluid and the first experiments that we did with it. So the task is now to take this system and bring it to this strongly interacting regime, this magnetic Feshbach resonance at 832 Gauss. So there's a few things, new things that come up with dual species experiments, which become technically challenging, and I have to mention them because they also end up allowing us to play a trick or two. So first, we know that gravity can be a big deal as the trap depth is lowered and you get into the quantum degenerate regime. The gravitational interaction becomes substantial compared to the optical trapping potential. And if you have a highly mass mismatched system, then the differential gravitational sag can be quite large. And in our case, the ytterbium gas, towards the end of evaporative cooling, has a significantly larger gravitational sag, and it droops down. The fact that we have two elements which have very different response to magnetic fields helps us fix this problem by simply adding a magnetic field gradient, which the ytterbium gas doesn't care about, but the lithium gas sure does. And we can use this now to tune the spatial overlap between these two species. Additionally, the addition of a magnetic field gradient changes the trap depth only for the lithium system. So you can selectively only evaporatively cool the lithium gas. So once you've brought the ytterbium gas into quantum degeneracy, it becomes not so good a coolant anymore because it becomes Bose-Einstein condensate, shrinks in size. The final part of the lithium cooling we do by this technique of changing the magnetic field gradient. And we arrange it such that this magnetic field gradient also brings the two species into good spatial overlap. Okay, so we observe the fermionic superfluid by moving the system from 832 Gauss over into a less strongly interacting area, about 690 Gauss or so. And then as the magnetic field gradient that is used for this evaporative cooling is tuned to different values, we see the formation of the fermionic superfluid here shows up at 690 Gauss as the formation of the molecular Bose-Einstein condensate. And you can see we get to a pretty pure system here. Together with the ytterbium Bose-Einstein condensate, then we now have a combined dual species Bose-Fermi superfluid. And this work, together with the experiments we did with it, are written up here recently on the archive. And I should also mention that recently another paper came out which reported on the achievement of simultaneous superfluidity in Bose-Fermi mixture of 41 potassium and 6 lithium. And that work, and there's a talk about that in this meeting tomorrow. So the characteristics, some of the characteristics of the system at unitarity are listed here. So the particle numbers on the 10 to the 5 scale, temperatures about half or less of the critical temperature, superfluid lifetimes of about a second. The geometry of the trap is kind of pancake-like. It's tight in the vertical direction and loose in the horizontal directions. And the relative sizes are the bosons are about a factor of 3 smaller in size than the Fermi gas in all directions. And the densities are listed here. The interspecies interactions are about 10% of the individual chemical potentials. So the interspecies interactions are small compared to the intraspecies interactions. So we study this system first by demonstrating the elastic coupling and measuring it by exciting dipole oscillations. And we selectively excite the ytterbium component by moving its center of mass diabatically in the vertical direction and then let it oscillate. We observe the oscillation in time of flight. And here is data showing the oscillation of this vertical center of mass position as a function of hold time in the trap. And we look at it in time of flight because the amplitude of the oscillation is so small in the trap that we wouldn't be able to image it. So we look at it as the velocity gets converted into position during the expansion. And we look at this oscillation compared with the oscillation when the Fermi gas is present. And we find that towards the, in red is the oscillation behavior in the presence of the Fermi gas. We find that at short times, they kind of start about the same and evolve. And then if you look at the long times, for sure you see a large phase difference between these two oscillations, telling us that something different is happening. You can extract the frequencies at the something like 0.1% level for these two and deduce that the fractional frequency shift is about minus 1.7% here. So first off, it's minus. And that tells us that the sign of this interspecies scattering length is negative. The sign was actually not known before. Earlier, only the magnitude was known through thermalization measurements. And the magnitude of the shift agrees with the mean field calculation. And for this data, I'm showing you the field is 780 Gauss, and 1 over KFA is about 0.39. So this gives us a picture of the S-wave interactions in the system, like so. You have this Feshbach resonance for the fermions, and then two essentially flat featureless lines for the bosonic interaction and for the Bose-Fermi interaction. And this one is weaker. It's about 13 Bohrs. And even though it's featureless, it does mean that it's a stable, uniform probe across the BCS-BTS crossover. Okay, so the last thing I want to tell you about is observation of a scissors mode in this Bose-Fermi superfluid mixture. And first, I want to remind you of what that scissors mode is. These are angular oscillations of a superfluid in an anisotropic trap and can be excited by diabatic rotation of the eigenaxes of the trap. The frequency of this mode is a quadrature sum of the frequencies of the two axes involved. And in time of flight, this oscillation can be observed as a time of flight of the tilt angle, as an oscillation in the tilt angle of the final Bose-Einstein condensate that you see. Now, this mode has been studied and proposed theoretically way back in 1999 by Stringari's group, and was studied in bosonic superfluids by groups of Chris Foote and Guccio, and also in fermions by the group of Rudy Grimm. In our case, we look at we see that there's a scissors mode of the bosonic component that is driven by the fermionic component. And the experiment is pretty much what I showed you earlier, this dipole oscillation experiment. But now, if you monitor the tilt angle of the final Bose-Einstein condensate image that you see, then you notice that in the absence of lithium, that tilt angle shows essentially no features, while if you look at the tilt angle with lithium, there is an oscillatory behavior, and if you fit it with a pure sine wave, you get a frequency which matches that of the dipole oscillation to within the uncertainty of the measurement, which is a few percent. And I'll note here that the scissors mode frequency is essentially the same as the vertical oscillation frequency because of the geometry of our trap being as squeezed as it is. The quadrature sum of this component and the horizontal component is the same as the vertical frequency to the percent level. We see the same behavior at another magnetic field shown here. And what's happening? So our understanding of this is, okay, the fermion center of mass is displaced a little bit from the bosonic center of mass in the horizontal plane. And as the bosons go up and down, there's a modulation of the torque, even from the mean field interaction of the lithium on the ytterbium. And this torque modulation drives this scissors mode basically on resonance. Why is there this little displacement? Well, there's experimental realities. There's small angular offsets between the trap axes and the magnetic field gradient from vertical, which defines gravity. So then when you've parked them on top of each other in the vertical direction, there may be a slight offset horizontally. And because the dipole oscillation frequency agreed well with the theoretical prediction, we can place a bound of how much that horizontal displacement is of about 0.4 of the Fermi radius. Okay, so I will summarize because I am in negative time now. I've talked to you about the creation of a ytterbium lithium Bose-Fermi superfluid mixture, talked about dipole and scissors modes we observed there, which showed elastic coupling and angular momentum exchange, further ideas for experiments, more collective mode studies, damping, sound, and of course, its behavior in optical lattice would be interesting to see as well. And I'll quickly mention that because of the large trap frequency ratio, you can imagine the ytterbium bosons may be a very good impurity thermometer extending to very low temperatures for the strongly interacting Fermi system. The controllable interspecies overlap that we showed also comes into play for future molecule experiments. Okay, and definitely thank the group. In particular, I want to point out Ricky Roy, who's been leading these experiments right here. And he had a poster yesterday. I hope some of you were able to see it. It was helped in these experiments by Elena Green and Ryan Bowler, and also Ben Plotkin-Swing, who's in the audience. He had a poster on atom interferometry work, which was today. And I hope some of you saw that as well. So thank you very much.
Thank you, Dr. Gupta. So this is the time for the question or comment. Anyone here? Let me ask the first question. So I must have missed something, but would you mention more specifically on the shape of the intensity that made this fast trapping possible?
Yeah, so it's so we control two parameters. One is the power, and the other is the size. Okay. So you can control. So initially, you want the volume to be large to load a large number of particles in, and then you want to shrink the volume down such that you preserve a high frequency, even though the power is coming down. So normally, in optical trap evaporative cooling, you lower the power and the trap frequencies also fall, and you have a problem having a high thermalization rate towards the end. So here you can ameliorate that by also dropping the size at the same time. So you keep a high trap frequency all the way as you proceed in your evaporative cooling. Okay, that's the basic idea.
Okay. Is there any other question from the audience? Okay. If not, then let's thank Dr. Gupta again. And also, let's thank all the speakers in this session. And we'll finish this session.
Okay, it's been a long day, and I'm suppose you are a bit tired. So we'd like to offer some